Hello, in this video we're going to find the central moments of X bar, and we'll do it for the first four. And the reason I'm doing this video is I'm creating a video called Approximating the Moments of a Function of X bar, and these derivations come into play, and so I'm pointing backwards to these to save time in that video. So here we're going to let the x's be IAD with some distribution, some density. The mean is mu and the variance is sigma squared. So when k is 1, it's the first central moment, which is this, and then the mean can be written as 1 over n sum of xi. So you take the expectation in, and that's a constant. You get this is mu, and then you sum a constant n times, the n's cancel, you get mu minus mu, which is 0. Now the second moment is this. So then I rewrite x bar to be this, but then mu can be written as a sum also, where it's 1 over n mu, because then this is a constant, so you'll get n of these, and the n's cancel and you get mu back. But we can do this, we can factor out the n since it's constant to both sides and get n squared. And then you can write this as one sum in here, the sum of from I to 1 to n, xi minus mu, and then that's quantity squared. So now let's square this, and you get this. So it's this times this. Well, this times itself with a different index, and then you take out, you combine the sums to the left. Now this one is interesting because when I and j are different numbers, it means this quantity and this quantity are independent, so you can take the expectation by itself. But we just showed that expectation is is 0. Well, this is x bar, but it's x has the same expectation, so this is 0. So it's only not 0 when these are the same value. So in a sense, we can just look at one sum and call those the same number. And that's what we do here. So it's the sum from I equals 1 to n of xi minus mu squared. But this expectation is sigma squared. Well, times n. But then one of the n's cancel, we get sigma squared over n. And now this is going from here to here, you got to make it straight. Maybe you write out some sums and look at it, because we're going to use this kind of property 2 more times. So let's look at the third moment, and I rewrite x bar to this, and then I rewrite mu to be a sum, and so I can take out the cubed and get n cubed, and then we're left with this sum cubed, the expected value of this cubed. So we multiply it times itself 3 times, and that's what we get here. Now the interesting part of this is when any one of I, j, and k are different, this is 0. So these could be the same value, but this is different, and then with the expected value of this times the expected value of that, but this is 0. So the only time that this is non-zero is when all 3 of the indexes are the same. So that's in a sense like getting rid of 2 of them and just using 1 and calling them the same thing. And that's what we do here. So we have 1 over n cubed, and we have the sum from xi minus mu cubed, but the expectation is a linear operator, so we can take it in. And this is, I'm going to call that mu 3, which is the third central moment. There's n of them, so one of them canceled, and we get this. Now to look at the fourth moment, it's a similar thing. We we factor out the n, and we have this raised to the fourth power. So we take it times 4. Now this, they can be different. If one of the indexes are different, it's 0. But if they're all the same, then we get the fourth moment. And there's n of them, and we get one of the n's canceled. But here, if 2 of them are the same and these 2 are the same, then we get something that's not 0. And so that's what we do. So if we there's n ways to pick the first index, then there's 3 ways to choose one of these, and then there's n minus 1 ways to choose that next index, and then the other 2 have to be the same. So we get, and then this expectation is sigma squared, this is sigma squared, and then this reduces to this. One of that n cancels with this, and that's it. And so that's the fourth central moment of X bar. And that's all I have for today. Hopefully you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.